So for the most part, the 2025 BCFRQ was a little unique in many ways. Um, it's it's often uh, very common to see a higher percentage of AB related topics in the FRQ section. But this year in 2025, we had a little bit of a change, and of course, the big shocker was in the calculator section when when we found out that we indeed have a polar FRQ after not having one for about 6 years, with mostly having parametrics. We do not have a parametric FRQ this time. And to be honest, that was expected. You got to expect a polar FRQ to come out sometime. But let's get right into it. So, this video, we're not going to cover any of these first 4 questions, but we're going to look into the 5 and 6 questions of the FRQs, which both deal with the Taylor series and infinite series unit for the most part. Okay, so let's figure out how to actually solve these FRQs, and I'm going to kind of walk through what you could have done to kind of get points and save time. Of course, the answers are not out, but we're still going to solve this together. So let y equals f of x be some solution to the differential equation. Okay, we have an initial condition, which I like to immediately write out as 1 comma negative 1. I just kind of like writing it that way. For part A, find f double prime of 1, the value of d squared y over dx squared, the second derivative at that point. So basically, we just need to take this for part A, take the derivative of the derivative. So derivative of this is essentially what we're doing. So if we do the derivative of 3 minus xy squared, we have to use product rule. So derivative of 3 minus x is negative 1 times y squared plus derivative of y squared is 2y, and you just multiply the 3 minus x. Then we want to find the second derivative at the point, so plug in 1 and negative 1, which you could just write as pretty much this. And essentially you would plug a negative 1 over here. It would just be negative 1, then it would be minus 2 times 3 minus 1 is 2. So negative 1 minus 4, which is negative 5. I believe that is the first part of this question that you would need to do. Just double check that that's all correct. Let me know, by the way, if I'm doing any calculation stuff here wrong. Just, because why not? But everything seems to be right. Okay. So for part B, write a secondary Taylor polynomial for f about x equals 1. So remember that a Taylor polynomial is written in the form where we have f of, let's say it's centered at, where is it centered at? Center at 1. So center at 1 would be something like this. And it would go on and on and on. Okay? So for this case, what you would have to do is first we want to find the initial condition f of 1, which we already know because we were told that f of 1 is negative 1. So they told us that. So t2 of x, the secondary Taylor polynomial, is equal to negative 1 plus we found the derivative at 1, which was negative 5. So it's more like minus 5x. And then we have plus the second derivative. Oh no, sorry, this is not the derivative at 1 is just dy dx at 1 comma negative 1, which in fact is just 2. So it'll be plus 2x. Then we'll have a minus 5x squared over 2 factorial, and there's your secondary Taylor polynomial. Okay? So there you have it. And we got this negative 5 from here. Awesome. So now we're going to move into the part C, which is the second degree Taylor polynomial for f about x equals 1 is used to approximate f of 1.1, given that this f triple prime of x is less than or equal to 60 for all x. Use the Lagrange error bound. So they told you that you're going to use the Lagrange error bound, which is kind of fascinating to show that this approximation differs most by 0.01, okay? So I'll do this part in red and up here to have the instructions. Here's how it works. So you say, remember, that the error is equal to the, in this case, right, we had a second degree Taylor polynomial. So it would be the n2 plus 1. So n here is 2. We went to the second degree. So the formula is f to the n plus 1 of c times x minus a to the n plus 1 over n plus 1 factorial. And in this case, it's f to the third, which because it's 2 plus 1, we went to the second degree Taylor polynomial. So the absolute value of f triple prime of c, some constant, times x minus 1, center at 1, to the third power over n plus 1 factorial, which is just 3 factorial. Now, here's the thing. We don't know what f... So this is the first thing you have to figure out, okay? Is basically what these numbers are. And once you know this, well, we don't know what f triple prime at some constant is. We don't know, we'll never know what that c is, right? If we knew what the c is, we would know the error and we would know the exact approximation, which makes no sense, right? So, okay. They told us this information right here, that the third derivative is less than or equal to 60, because remember, and I should rewrite this, error is equal to the maximum of the f to the n plus 1 derivative, okay? So here's how it works. So what you say is you basically say that the error, so let me rephrase this, guys. I apologize. So the error is equal to this, okay? This is the error. But we don't know what that c is, but we can show that it's at most some amount. So error, in this case, is less than or equal to the maximum of f triple prime at some c, right, times x minus 1 cubed all over 3 factorial. And so our estimation here by using this polynomial is off at most by this. And they told us that f triple prime of x is always less than 60, no matter what, on this interval from 1 to 1.1, which is the only interval we care about. So no matter what this c is, we know that it's going to f triple prime at whatever number for whatever c in between 1 and 1.1 is always going to be at most 60. So then you follow with an equal sign. Make sure you, if you're going to do this, follow the equal sign after you set the inequality. Otherwise, you're going to get points off for notation, right? Saying that this is less than or equal to, again, is incorrect. Hopefully you guys noticed that. Nothing too crazy though. So it's less than 60 times x minus 1 cubed over 3 factorial. And this is the maximum error. Now we are using the for the approximation of 1.1. So we're trying to see how much the error can be at most if we plug in 1.1 to the x, okay? So plug in 1.1, and in this case, you plug in 60 times 0.1, 1.1 minus 1, cubed over 3 factorial is how much the error is at most off by. And what would happen is that you would see that this, in fact, is just equal to 3, it'll be 10 times 0.1 cubed. And this right here is just 0. Pretty much, right? Because this is 1 over 10 to the third power. Well, one of the 1 over 10s will cancel, so it's just 0.01. And so there you have it. And that's all you have to write. This is all you have to write. And you simply mark that it's 0.01, and they know that it's at most, okay? So there is part C. That's how you do it. And the key was to remember the Lagrange error formula. let's do the last part here, which is part D, using Euler's method, approximate f of 1.4. So from here, just it's a standard Euler's method problem. Now, in this case, there's people that do very different methods of Euler's method. So the way I do it is that for every next step, I use the previous step's y value times the step size times dy dx at the previous coordinates. So I use this formula for Euler's method, okay? So this is my way of doing it, right? So remember that x sub 0 is equal to 1, right? It starts at x equals 1. Y sub 0 we know is negative 1. And we want to approximate f of 1.4, okay? So first, I do f of 1.2 is approximately y sub 1, which is equal to y sub 0, so negative 1, plus, and remember, h is always going to be, we have a step size of 0.2, I believe. Yeah, of 2 steps of equal step size, so the step size is going to be 0.2. To get to 1 to 1.4, right? Because remember, if we only go to 1 to 1.4 with 2 steps, it's just the difference between them, which is 0.4 divided by 2, okay? So the height here, or the change in x, is going to be 0.2. So negative 1 plus 0.2 times the derivative at 1 comma negative 1, which we did find earlier, which was 2. And this is, we use the Taylor series right here. So the derivative at 1 comma negative 1 was 2, which is just equal to 0.4 minus 1, so negative 0.6 is our first movement. So now we know that x sub 1 is 1.2, and x and y sub 1 is negative 0.6. Now we do this again for the last part, which is f of 1.4, which is approximately y sub 2, which is equal to y sub 1 plus h dy dx at that previous points. So it'll be y1 negative 0.6 plus 1. Let me make sure here. It'll be, I know it's 0.2 times the derivative at the previous coordinates of 1.2 comma negative 0.6. So you would find that. And give me a second here. So we plug in 1.2 and negative 0.6 into the derivative. So 1.2 here and negative 0.6 there. And this is just annoying math at this point. It's going to be 1.8 times negative 0.6 squared is is 0.36, I believe. Whatever that gives us. 0. And there you have it, guys. Just leave it at that. You don't have to do any arithmetic. You can leave it unsimplified like this. So there you have it. So there is how you do Euler's method in my case. Okay. So pretty, not a bad problem in a sense. Lots of concepts you had to just memorize, like Euler's method and Lagrange error. But as you see, the work that I took up is not entirely too much, right? So nothing too crazy there. For part 6, which in my opinion is somewhat easier. So what I would, so the part A and B we'll do really quickly, and particularly this one is a very standard FRQ question. Nothing really too insane here, guys. So we have some function that converges to f, right, on its interval of convergence. So we want to find the interval of convergence about for f about x equals 4. You don't have to worry about that. It is already about x equals 4. So for part A, we're going to do the limit as n goes to infinity of the absolute value. So this is the series that we're going to do the ratio test for, okay? This is just your standard ratio test technique. So it's going to be x minus 4 to the n plus 2 over n plus 2 to the times 3 to the n plus 1 times, and then the reciprocal of the original. So it'll be n plus 1 times 3 to the n over x minus 4 to the n plus 1. Okay, so we're going to find this limit. This is the same thing as the limit as n goes to infinity of x minus 4 times n plus 1 over 3 times n plus 2. Okay, hopefully you guys saw how we got that. We did some canceling here, right? These two will cancel. This will go away. The 3 to the n will leave a 3. And then these two are just remaining. Don't forget the absolute value bars. And this limit is simply a rational function limit. We only care about this ends. Ignore any term connected to the x. Just forget about it. Just ignore it. Think about the limit. It's the limit for ends. Okay, so this guy is what we're caring about. And this limit is like a horizontal asymptote for a rational function, right? Remember that the limit as x goes to infinity of something like x plus 1 over 2x plus 1, right? You guys remember this? It's just the ratio of the coefficients, right? So you do the same thing here, and in this case, the ratio of the coefficients, when you account for this 3, right? Imagine you distribute this. Well, that's just going to be, it's going to be 1 over 3, right? There's one n here. The coefficient here is 1 on the top, and the coefficient on the bottom is 3. Okay, so it'll just be equal to absolute value of x minus 4 over 3. That's it, okay? Now, we set this less than 1. So that means that x minus 4 over 3 is less than 1 and greater than negative 1. So this also means that if you multiply both sides by 3, you get negative 3 is less than x minus 4 is less than 1. Or so 3. So, and then you add 4 to both sides. So 1 is less than x, less than 7. There's your interval right there. But hold on a second. This is no, we're not quite done yet. To see, essentially, if the endpoints here at 7 and 1 are included in the interval, we have to plug in 1 and 7 to the original series, okay? So I'm going to do this part in pink. So let's look at the case when x is equal to 1. So for the summation, it'll be the infinite sum from n equals 1 to infinity. If we plug in x equals 1, we get negative 3 to the n plus 1 and n plus 1 to the 3 times 3 to the n, okay? So this is our new series that we have to look at right here for plugging in x equals 1. So now we have to see, does this converge? And this is where we use our good old series tests, okay? So for this problem in particular, just notice that we can kind of say that I'm going to ignore the summation sign for a second. This is the same as negative 3 to the n times negative 3 over n plus 1 times 3 to the n. And furthermore, I can expand this again to 3 to the n negative 1 to the n, right? And these two cancel out. So this is the same thing as the infinite sum of negative 1 to the n times negative 3 over n plus 1. And now we have a good old ratio, alternating series test. So we check that it's a decreasing sequence, which it is. I'm not going to show that. And then for the really important condition, just know that the limit as n goes to infinity of negative 3 over n plus 1, the alternating series says just look at the part without the negative 1 to the end. Just kind of cross this out of your mind and see, take the limit of that, okay? That's the alternating series test. And this, of course, goes to 0, so we pass the alternating series test. And, of course, you would have to also, in the test, argue that this is a decreasing sequence. I'm not going to do that. And honestly, it's kind of a stupid rule because if the limit goes to 0, it probably means it's a decreasing sequence. And in all cases, it is. But, you never know. Okay? So x equals 1. For x equals 1, the series converges. So we definitely include that in the interval here. The next thing we're going to look at is for x equals 7, which is going to result in 3 to the n plus 1 over n plus 1 times 3 to the n. Okay? So now we want to look if this series converges. For this series, this is the same thing as we can now cancel at least one of the 3's, leaving a 3 on the top. So it'll just be 3 over n plus 1. Lots of ways to do this one, guys. The first thing is you can do an integral test here, which is quite difficult, more work. The second thing you can do is you can basically say that compare this by direct comparison to 3 over n, which diverges by p-series test for p greater than 1. Sorry, less than or equal to 1. I'm sorry. Apologize for that. So there you have it, guys. Apologize for the handwriting. I'm using a really big font, but you get the idea. So this just diverges. Okay. So the interval of convergence indeed is this, and you would state that interval. We don't include the 7 here, and you would state that interval in more formal writing. But let's move on to part B. I'm going to move this all this craziness up here so I don't have to worry about it. Okay. So for part B, find the first 3 non-zero terms and the general term of the Taylor series for f prime, the derivative. Okay, so this is how you do it, guys. Instead of taking the derivatives individually and then finding a general term, which is too much time, first rewrite the sum. Okay, so remember f of x is equal to the infinite sum from n equals 1 to infinity of x minus 4 to the n plus 1 over n plus 1 times 3 to the n. Okay, this is our summation. F prime, we just apply the rules inside the summation. Okay, it's the same sum. Now just take the derivative of this with respect to x. Okay, so it'll be n plus 1 times x minus 4 to the n, right? That's the power rule on the top. And everything on the bottom just stays there. There's no x's on the bottom. There's nothing to worry about. Okay, so that's f prime of x. And you would say for the first 3 non-zero terms, you would just plug it in. So plug in n equals 1. It'll be, is it about anything? For about x equals 4, yeah, nothing. Okay, so the first non-zero term, so plug in 1. The first term, if you plug in 1, you will get 2 times x minus 4 over 6 for the denominator. Plus, plug in 2, you'll get 3 times x minus 4 squared over, and then 3, so 2, 3, 9, 27. There we go. Plus, for the plug-in n equals 3, which is going to be 4 times x minus 4 cubed over 4 times 27, which I don't know what that is, but you can just leave it at there. And so those are the first 3 non-zero terms, okay? So there you have it. That's all you need to do for part B. For part C, the Taylor series described for f prime is a geometric series for all x. Show that it converges to x minus 4 over 7 minus x. So the way you want to do this, pretty much. And what I just realized was we could have always just canceled this out, which is very annoying. And we would have gotten the same result. So be a little smarter, but anyways, the answer is still the same. These would cancel out to 1 and 3, and on and on and on. For part C, the Taylor series f prime is geometric. Okay, so the series that we were interested is this following series, pretty much, and this is equal to the infinite sum from n equals 1 to infinity. If you use the properties of exponents, you can notice that this is the same thing as this. Okay, so know that these two are the same. And this is a geometric series now, right? It's a times r to the n, where r is x minus 4 over 3. So the sum, remember, is equal to a1 over 1 minus r. In this case, we have a1, which is just x minus 4 over 3. That's the first term in the sequence, over 1 minus x minus 4 over 3. And this indeed will show to x minus 4 over x over 7 minus x. Okay? And you can do that on your own mathematically. And for part D, it is known that the radius for about x for the f of convergence of the Taylor series for f is the same as the radius of convergence for a Taylor series of f prime. And does the Taylor series f prime converge to f prime of x at x equals 8? Well, you can argue two reasons here. Okay, the answer is no, absolutely not. First, the interval of convergence earlier for f is for all x on the interval from 1 to 7, not including 7 and including 1. That's the first part, and this is a fancy way of writing it. And the other way you could write it is to simply plug in. What you would essentially do is that you would plug in x equals 8 into the series of f prime, which is just infinite sum from n equals 1 to infinity of 8 minus 4 over 3 to the n. And this inner summation part is the same as 4/3 to the n, which diverges since the geometric series has r equals 4 over 3, which is greater than 1. Okay, so there's two ways you could have really argued this, and yeah, so there you have it, guys. That's pretty much all you need to really know for this these two FRQs. Not horrible, definitely not horrible. Could have been worse, way worse. In fact, parts C and D, all you had to just notice was that this could have been rewritten into this f prime power series can be rewritten in the form of a geometric series. So yeah, and part D, there's literally two ways to approach this, right? So there you have it. And of course, give a reason for your answer. Just make sure you explain this really well, right? This one diverged for a geometric series, and it for x equals 8 is outside of the interval of convergence, okay? So there you have it, guys. That's all you need to really know for these two questions. Not horrible, guys, not horrible. And so for calc students next year, just make sure you really get your Taylor series and Maclaurin series and power series stuff down, okay? But this stuff, it's all stuff you've seen in your classes, and if you haven't, your teacher has failed you. But I hope you guys did great on that exam, and thank you so much for watching this video.